So this week's work is based around the concept of planar graphs. Let me go straight into the definition. We have come across this before, but a graph is said to be planar if it can be drawn in such a way that edges only intersect in vertices. There are no unauthorized crossings of edges. The problem is that it's often, one can represent graphs in many different ways, and often you come across a planar graph, first of all, drawn in a way that doesn't make it obvious that it's planar. We saw that for the octahedral graph. We saw, in fact, two ways of drawing it with lots of crossings, but it is, in fact, a planar graph. So if you do have a representation of the graph in which the only edge intersections are in vertices, you call it a plane diagram. So we can easily understand this concept with the example of the complete graph K4. So K4 is the graph on 4 vertices, and it's the same as the tetrahedral graph. In fact, you can draw it as if you're staring at a tetrahedron. So we have our 4 vertices, and we have our 6 edges. That's the tetrahedral graph, or K4. And that is a plane drawing of K4. But one knows you can also draw K4 as a square in which with diagonals, but you must, in this drawing, the crossing of the diagonals is not a vertex. So that's what I called an unauthorized crossing. That's also K4. But only the one on the right is the plane diagram of K4. Once you go to K5, the complete graph is no longer planar. Similarly, K2n, for any n, is a planar graph. There's a picture of K211 on the Keats page. But as soon as you go to K33, it's no longer planar. So the two basic examples of non-planar graphs are K5, the complete graph on 5 vertices, which, as I explained before, is a bit like a pentagon with a pentagram put on top of it, and K33, which is the utility graph in which you're trying to connect water, gas and electricity to 3 houses. Let me actually give you a non-conventional picture of K33, or less common picture of K33. You can get it by just drawing the 6 verticals around a circle. I haven't got enough here. Should have spaced them equally. And then actually drawing edges between the opposite vertices. But the idea here is that the triple cross in the middle, that's not a vertex. It's not the wheel graph in which there would be a vertex in the middle. This is K33 with 6 vertices and 9 edges. 6 around the outside in this picture and 3 diagonals. But that's not a planar graph. There's no way you can put one edge, you can get rid of one edge and say put it round here, but you can't get rid of the remaining crossing. It's impossible. So we're stuck. I can't move one of the other edges. It's going to cross this new edge on the outside. So K33 is not a planar graph. Now, I'm going to be talking about the Platonic graphs, that is, the graphs coming from the 5 Platonic solids, the edges and vertices of Platonic solids. And these will also be planar graphs. We saw them briefly before in the first lecture in week 4. And there's another talk after this that goes into their properties in much more detail, and I'll be drawing diagrams there. I won't attempt, other than K4, I won't attempt diagrams. I won't attempt to draw the Platonic graphs. I'll just show you the solids on which they're based. In fact, you can take any what's called convex polyhedron and get a planar graph out of it. So a convex polyhedron, it's best understood by sort of bringing a number of planes in from infinity to get a finitely bound, get a solid of finite volume, and that will be a convex polyhedron, it will have the convexity property that given any 2 points on the solid, the whole straight line between those 2 points lies in the solid. And you can think if you have a convex polyhedron, you can sort of blow it out into a balloon, if you like, and represent it on a balloon or on a sphere. And then if you just take 1 point on the sphere that's not on that's in the middle of a face, you can sort of project the whole sphere down to the sort of equatorial plane, and that gives you a plane diagram of the edges and vertices of your convex polyhedron. But I'm just going to show you the famous or the celebrated Platonic polyhedra, and here they are. The photograph is mine, so that means one doesn't understand very much. But I hope you know them by name, or you should get to know them by name. There's the tetrahedron. There's the octahedron at the back, that's sort of a diamond lying on its side. There's the cube, of course, at the front. And then on the right-hand side, there's the icosahedron with triangular faces, 20 triangular faces, right bottom right. And there's the dodecahedron, which has 12 pentagonal faces, top right. So the Platonic solids, these 5 solids, are special types of convex polyhedra. They are the convex polyhedra in which all the faces have the same size and shape. So in particular, each face is corresponds to a regular polygon with the same number of sides for each face. And I'll show you in the next talk, I think, that that fact alone will show that there are only 5 possibilities. I mean, in the graph theory, we're not interested in the fact that all the sizes are the same. It's the fact that all the faces are polygons with the same number of sides. And it turns out you can only have 3, 4, or 5 sides. As represented, 3 of those 5 solids have triangular sides. It's triangular faces, I should say. So those are the Platonic solids. Let's just look at them individually. So I don't need to say much more about the cube. We've seen the graph formed by the edges and vertices of a cube. It's a bipartite graph, chromatic number 2. Sometimes called the hexahedron because it has 6 faces. That's somehow dual to the octahedron. You can sort of put a vertex in the middle of each face of the cube, and then you get an octahedron. So an octahedron has 6 vertices, but 8 faces. You're swapping vertices and faces, and the faces become triangular. And we've also seen its graph in different representations. In some sense, my favourite one, because it's sort of easy to remember and even to draw, is the dodecahedron. So this has, in the picture there, you can more or less see that it's standing on one pentagon, and it has 2 rings of pentagons and 1 at the top. That's a 1 plus 5 plus 5 plus 1, 12 faces, which are all pentagons. And that's dual to the icosahedron, in which you swap vertices and faces. So the icosahedron has only 12 vertices, but 20 faces, which become triangular. And then a special, because the easiest one in a sense is the tetrahedron, whose graph corresponds is just K4, and that has four faces and 4 vertices. So if you try and put a vertex in each face and get another graph, it would just be a tetrahedron. It would just be K4 again. Or in terms of solids, you can say the tetrahedron is sort of dual to itself. So those are the 5 Platonic solids. But it's, as I just want to emphasize, it's the graphs we're interested in, the graphs formed by their edges and vertices. We've seen 2 of them. We've all seen the dodecahedron as well when we were colouring vertices. We removed actually 1 edge of them. We've seen K4. So the only one I haven't drawn to date, I think, is the icosahedron. Okay, I just want to give you examples of polyhedra which are not Platonic solids, just for fun, just to emphasize the conditions one puts on to get the Platonic solids. So the important condition is they have to be convex. So the first two polyhedra on the left are not convex. You can find points, you can easily see that you can find 2 points on the surface of the solid for which, if you take the straight line between those 2 points, it does not lie in the solid. Think of just taking a phone wire, a cable, and pulling it tight between 2 points. So in both cases, the wire goes outside the solid, so the solid is not convex. They're quite easy to describe. The second one, for example, the small stellated dodecahedron, is formed by taking an ordinary dodecahedron and plonking down on each pentagonal face one of these sort of pentagonal pyramids. So it's just a lot of small mini pyramids on the dodecahedron. So they fail because they're not convex. They're not in Plato's list, if you like, because they're not convex. On the other hand, the picture on the bottom right, that's formed by starting from a cube and sort of slicing off the corners exactly to halfway along an edge. So the 6 vertices of the cube become the 8 vertices of the cube become triangles. So you get 8 triangles instead of 8 vertices, and you're left with 6 smaller squares. So this fails because it has not all the faces are the same shape. You've got a mixture of triangles and squares. So that would be called a truncated cube. It is convex. In fact, it's the smallest convex solid that contains those black vertices you can see. Okay, and then there's another famous example, I can show if I remove my pad, of a truncated polyhedron, which is this example here. This is a truncated icosahedron. So football actually was introduced in the Mexico City World Cup in 1970, and similar designs used afterwards. The idea is we've taken an icosahedron, we've shaved off each vertex. So the vertices of an icosahedron have degree 5. So if you shave off a bit of the vertex, you're left with a pentagon. So you've got 12 pentagons in this configuration, and the remaining faces, the residual faces, become hexagons. So this football consists of 12 pentagons and 20 hexagons. The truncated icosahedron. Okay, back to the theory, and I want to now talk here. The work is perhaps more important for the course. I want to talk about Euler's formula for both polyhedra and therefore for the graphs that they define, polyhedral graphs. So Euler's formula is simply this, that let's first of all state it for polyhedron. It just says that the number of vertices minus the number of edges plus the number of faces is equal to 2. Okay, that's the formula. And I'm actually going to verify it for the football. So if we consider the case of the football, you need to sort of do a little bit of extra work. But for the football, we have, so let's see, we have n the number of vertices. Well, there were 12 in the icosahedron, but each one gets replaced by a pentagon, so that gives 60 vertices. The football has 60 vertices. The edges you can actually work out by, you can, if you like, just take the pentagons. There are 12 pentagons, that gives you 60 edges, and then there are 20 hexagons, that gives you 180 edges. So 120 edges, 20 times 6, 120, and you add those together, that's 180, but you have to divide it by 2 because each edge gets counted twice. So the number of edges is actually 90, and the number of faces, well, I told you that there are 12 pentagons. The number of faces is equal to 12 for the pentagons, plus the number of the hexagons, which corresponded to the original faces, and there are 20 of those, so that's 32. And that will work out 60 minus 90 plus 32 is equal to 2. So that's the formula for quite a complicated polyhedron. But when you apply this to graphs, you can apply it to the graphs, the plane graphs. You take a plane drawing of a graph and the faces become regions. But you have to remember that you add one, you include the outside region as a face. So F represents a number of regions in your graph, including the infinite outside region. And then Euler's formula is valid. So I want to prove this, and I'm going to prove it by induction on the number of edges in a graph. So let's take the simplest possible case in which we have 0 edges. I did promise not to talk about this ever again, but it's quite useful in this situation to consider having 0 edges to get the induction started off. So because this is a connected graph, and this theorem only works for connected graphs, easy to see it will fail if the graph's not connected. Because the graph is connected, we can only have one vertex. We don't have any edges. We can only have one single isolated vertex. And so obviously that means that n is equal to 1. We've got no edges. E is equal to 0. I won't write that. But we do have one region, in the sense we have the outside region. So F is equal to 1. So 1 minus 0 plus 1 is equal to 2. So that satisfies Euler's formula in a silly way, but it works. And then we use induction. So we suppose that the formula is true for any connected plane drawing with a certain number E of edges. And now we suppose that there's one more edge. So if you like, we get, let's say, a bigger graph with one more edge, and we can try to reduce to a graph with E edges by removing an edge. So if we do that, we can see that we can, so we try and remove, so we're given a graph with one extra edge and we try and remove it. So, and there are two situations, two scenarios. It may be that we have a graph here in which we have, let's see, maybe we have, here's a part of the graph here, and we have what I've called an edge with a free end. So here's an edge with a free end. A free end means vertex 1. There may be other bits of the graph we're not interested in, but we have an edge with a free end. Now I want to remove this edge here with the free end, but because I need to have a connected graph, I also have to remove the vertex, the free vertex, which isn't attached to anything else. So I remove both the edge and the vertex. What I've done is I've removed one edge and one vertex. So I've removed one edge and one vertex, but n minus e will not, because of that, n minus e will not change. Okay, so I don't change. If this formula worked for the smaller graph, it will still work for the graph with one extra edge and vertex. Another thing I could do is I could suppose that, well, let me draw it before I refresh the text. Maybe I don't have a free edge. Maybe all my edges, I don't have any vertices of degree 1. So maybe I've got an edge which goes, say, between, crosses a face like that. So this is an example where I don't have a free edge. So I can still remove this edge. But what I've done if I remove this edge is I don't need to remove any vertices. But once I remove that edge, I have converted two faces into one face. I now just have a single face, which is here. So what's happened on this occasion is that this time I haven't changed the number of vertices, but I've kept the quantity minus e plus f the same, because the extra I've reduced by one edge, but I've also reduced by one face. So minus e plus f stays the same. So also in that situation, I've preserved Euler's formula. Okay, so that's what I've written. And so in both cases, the left-hand side, n minus e plus f, stays the same. Okay, you might also see this sometimes written as, I use n for the number of vertices, but some people might use capital V, so you might see this written capital V minus e plus f. Remember, when you come to graphs, f is the regions rather than faces, but you must count the outside. Plus f is equal to 2. Okay, that's Euler's formula. Okay, one more example, just to remind you, count the outside. We could take K4 again that we started with today. That's a planar graph, 4 vertices, no edge crossings except in the vertices. How many vertices are there? 4, obviously. How many edges are there? 6. How many faces? Well, the key thing about the faces is that there are 4 of them, because you mustn't forget the outside. You can also think of this sort of looking into a tetrahedron. So in a sense, the outside face is like sort of counting the face you're looking into. So anyway, this is plus 4, so the total is again 2. That's applying Euler's formula to a planar graph, or planar diagram, I should say, plane diagram of the graph. Now, I just want to finish with 2 facts. And to be honest, I'm jumping forward here to 6.4. There isn't an awful lot in 6.4 in the notes which you need to read, but this first proposition is extremely important. And I'm not giving the proof here today, but you can easily look at the proof in the notes. And it's just a consequence of Euler's formula. So it says that if we have a simple planar graph with at least 2 edges, then the number of edges is less than or equal to 3 times the number of vertices minus 6. You do need more than one edge, because if you just had one edge, then the formula wouldn't work, because it would tell you if you have just one edge, it has to be connected, this graph. So one edge means 2 vertices, and then the formula would, if it were true, it would tell you that 1 is less than or equal to 6 minus 6, which is 0, which of course is patently false. But the reason that goes wrong is that somehow your region, we've only got one region here, the outside, is only bounded by one face. To get this formula to work, you need to assume that every region is bounded by more. So it's only one region is bounded by one edge, I should have said. Similarly, you can't allow graphs that are not simple. That would also fail, because you'd have 2 edges joining the same vertex. And in that case, let's see what happens in that case. We would have 2 regions, but the number of edges is equal to 2. And that's even worse. We'd have 2 edges less than or equal to 3 times the number, well, again, less than or equal to 0, which again is false. So we have to rule out those possibilities, but if you do rule out those possibilities and assume the graph is simple, you get this formula. And incidentally, this will imply, if we didn't already know, but we do, that the complete graph K5 is not planar, because it fails to satisfy this formula. It's not true that 10 is less than or equal to 15 minus 6. You can also rule out K33, but that needs a slight strengthening of this proposition, which is done on sheet 6. Okay, the last result I want to give you follows. It's very easy to result to remember. but it follows from a very deep theorem in mathematics, the so-called Fourcolor theorem for maps, which you may have heard about. It was proved about 45 years ago, proved by computer actually, or with computer assistance. And that tells you fairly immediate consequence of this theorem is that if we have a simple planar graph, it is four-colorable. That is, its chromatic number is less than or equal to 4. So certainly don't expect you to prove this theorem, but you should know the result. So if you know that a graph is planar, even if you don't have a planar representation of it, you know that its chromatic number cannot be bigger than 4. And needless to say, it follows that the Platonic graphs all have chromatic number less than or equal to 4. Some of them have chromatic number equal to 4, as we'll see in the next talk. Okay, so as regards this week, the talk today and the next talk, I think, are fairly light. There's a lot of descriptive stuff in them. The real meat in terms of the mathematics comes when we discuss in following on the criteria that tell you when a graph is planar or not. So we'll see that if a graph is not planar, it must contain, in some sense, either K5 or K33. And understanding what I mean by contain will lead us to talk about subgraphs and also contracting edges in a graph. So we'll discuss theorems that tell you when graphs are not planar.